Welcome to Virtual Humans Lecture 8.1, Vertex-based clothing. This is part 2, people in clothing from images. So in the last lecture, we saw how to represent clothing using vertex displacements. And then we saw how to use this representation to obtain registrations of scans, including people in clothing. And we saw how to change the representation to separate the clothing into separate garments and estimate the body shape under clothing. In this part, we will see how to estimate 3D human models of people in clothing from images. So back in 2018, it was not possible to reconstruct automatically 3D models of people in clothing. And this is perhaps the first paper that demonstrated that this was possible. So in this case, this paper was assuming a single video of a person rotating in front of the camera. And the goal here is to reconstruct like an avatar, like what you can see here, which can be edited in terms of pose and shape. So the basic idea is based on optimization, right? So the first thing you might think is, well, I have a video and the clothing and the shape of the person barely changes when we rotate or when we move, because the only thing that changes is the pose. So one idea might be, okay, I can set up an optimization framework in which I optimize the pose, the shape, and the clothing displacements over all the sequence. Now I'm going to have one pose, theta I, for every frame I, right? And for every frame, I'll have like a measure of how well my model fits the data. This is similar to this paper that we saw in the previous lecture in sparse inertial poser, where we were using IMUs. Here we're using images. So the fitness measure is basically some distance of the rendering R of the model M that depends on the parameters that we're optimizing over, theta I, beta, and D, and the image itself, right? And this distance measure might be a silhouette overlap or the overlap of joints or like comparing edges, things like that, right? Comparing predicted features with detected features in the image. Now, one problem with this formulation is that you have to optimize all the poses at once. So this is like, in principle, it's slow and it's memory intensive because you have to load like all the simple models for every frame, right? You need one model for every frame and you need to update all these models simultaneously. And this is typically memory intensive. It can be done efficiently, but it typically requires writing specialized code for this optimization, which is perhaps not very convenient. So there's another way of looking at this problem, and this is what it was shown in this paper from CVPR 18, which was called, it goes under the name of video avatars. So there is a classical computer graphics technique to reconstruct 3D shapes from multiple views, which is called visual hull reconstruction. So basically, like a standard visual hull assumes a static object and multiple views looking at the object, as you can see here. And then like what you can do is like you can shoot rays from each of the camera centers. These are the camera centers. And you can shoot a ray that goes from the camera center to the silhouette, right? One of the silhouette points. And this creates what is called like a silhouette cone, right? It's a cone that goes through the silhouette. And now by intersecting these cones, you can obtain the 3D shape. Another way of looking at it is you can like voxelize the 3D space, and then basically you project the voxels into each of the camera views. And if it's overlapping with the foreground, it means that it's part of the surface interior. If it's not, it means that it's part of the surface out. It's part of the background. And like this, you can reconstruct the surface, right? This is visual hull reconstruction, very simple algorithm. The problem, however, is that the person is moving here, right? So the poses are changing, so we cannot assume a static object. So we need to compensate for this. And notice that we know how to estimate the 3D human model using the simple model at every frame, but we do not capture these clothing details. So notice that the simple model does not explain the clothing. So what can we do about this? What can we do to estimate the clothing and without having to optimize for all the poses at once? So the idea is basically based on the visual hull, and in plain terms, what is being done here is to generalize the visual hull to articulated objects. So the visual hull assumes a static object here. We're not going to make this assumption. We're going to relax this assumption and allow the object to move according to articulation. So here, the silhouette rays, right, are shown, right, that go through the camera center and the silhouette. And then basically you can obtain a correspondence to the surface of the model, right? These are these arrows indicated here. So every ray is associated with a single body model point. And what we're going to do now is to unpose these rays that go from the camera and the silhouette in order to optimize a single shape regardless of the pose, right? So you remember this unposing trick that we did to learn the simple model. This is like, perhaps you could think of it as a generalization of this when you have like not the full 3D scan posed, but you have just the silhouette of a person. So here's the idea. You shoot this race, associate the race with the 3D model point, and every 3D model point deforms according to the kinematic chain corresponding to this point, according to the simple model. So basically, like now, the rays are gonna deform jointly with the simple model. So we are unposing the rays. So why would we do such a crazy thing? Well, the cool thing now is that these rays are setting up constraints on where the body can lie in space, right? But they do not depend on the pose, because now we have unposed the rays, right? So the key idea is to transform the silhouette cones according to the inverse of non-rigid motion. How does this look mathematically? Well, we have like a ray in the canonical frame. This is what we want to obtain, R. And we have the ray in the post frame, which is R prime. So what we need to do is to apply the inverse transformation, right, that is applied to the vertices of the model. So this ray will be associated with a vertex. This vertex will have like its transformation matrices JK and its blend weights WKI. And so basically this linear combination of transformation matrices that come from linear blend skinning needs to be inverted. That's why you have this -1. And then after inverting the articulation, you need to invert, subtract the contribution of the post blend shape. Okay. So essentially, this is like moving a vertex forward, but moving it backwards, and not applying it to a vertex, but applying it to a ray, right? The line. And once you've done this, right, you have transformed the rays in the canonical, in the post space to the canonical space. And this is an idea that like hopefully is starting to become familiar to you because it appears over and over. This is the idea of unposing in order to estimate the properties of the shape regardless of the pose, which is the same trick as what we did for learning the simple model. And we will see this trick happening more often. Here, perhaps like it's slightly more interesting because we have like these rays and these constraints that come from silhouettes. So now here's the basic optimization. Now we have like an arc mean over the shape parameters, only a set of shape parameters, because we assume that the shape is constant over time. That's in practice not exactly true, but you know, it's a reasonable assumption. And we have like the optimization over the displacements for the clothing, so which is also assumed constant over the sequence. So what is the data term? Well, this is going to be like the distance from the rays to the corresponding vertices in the model. And this is given by this equation over here. This is a point-to-line distance of the ray expressed in Plucker coordinates. You don't need to like get into these details, but just believe me that if you do V cross product Rn minus Rm, where the rays expressed in Plucker coordinates, you have like a sum of point-to-line distances. And then the prior terms are basically enforcing symmetry in the shape. And we have a prior on the shape, which is based on this PCA space of the simple model. And then we have surface smoothness over the shape, which, if I recall correctly, this is also based on some Laplacian regularizers, as what we saw for cloth gap. And maybe I should mention, let's go back here. So notice that once we have imposed the rays, this objective function does not depend on the pose. And this is great because now the optimization is much quicker and it will produce the desired results without having to optimize over pose. Now, the trick here is that, of course, if you have wrong poses, then this shape optimization will not be correct. So you have to make sure that the poses are accurate in the first place. But that might be difficult if you don't have a good shape model in the first place. So you have a chicken and egg problem, which you might solve by fitting the poses once, optimizing the shape, and then refitting the poses. But in practice, the poses can be reasonably can be obtained reasonably even when you don't know the shape of the person. And so applying this method, like one leverages the temporal information, and we can recover the 3D shape of the person and along with the poses. And so these results were, when we obtained these results, we were quite happy and we were quite impressed by the quality of the results. Nowadays, you can get much more detailed reconstructions and even from a single frame. But this was cool because it was a demonstration of what was even possible using the state of the art that we had at that time. And yeah, so basically, one can use this method to reconstruct a wide variety of people in clothing, not very wide clothing, but notice that, you know, there's some large hair variation and like wide clothing, but like things like skirts and so on, because we're based on displacements, it's not, it wouldn't, like the quality wouldn't be very good. And because this stems from the simple model, like then you can apply poses to these avatars and you can make them change the pose. And you can also change the shape of these avatars, as it's shown here, right? Because the displacements are applied on top of the simple model, so you only need to change the simple model in order to change the shape of these models. All right, so this was an optimization-based method, and even better details can be obtained using a method that is based on shape from shading. If you're interested in this, you can check the literature on shape from shading. It's basically looking, trying to estimate jointly the normals of the surface and the light sources in order to figure out like the details of the 3D shape. But again, this is like based on optimization, and it's fairly involved. So basically the limitations are that the optimization can be stuck into local minima, as we've seen for other methods. And perhaps the biggest limitation is that clothing as a single offset is limiting because you cannot separate the body from the clothing. So you can, for example, not retarget clothing from one body to another, right? That's some limitation. And the other limitation is that, of course, it might get stuck into local minima. So there's no like real learning here other than just detecting the key points of the body in 2D in the images, right? And segmenting the human body from images. So then later, 1 year later, what people started looking into, including our group, is basically like departing from the purely optimization methods and like including learning. And essentially this, you can think of this as adding a front end, right? That given the image will predict like the parameters of the model. And then you're going to train this. If you do not have 3D data, you're going to train this using a self-supervised loop where you start from images, you predict these parameters of your 3D model with a convolutional neural network, and then you push this through a 3D differentiable model, like simple, plus displacements, and then like you have the 3D model of the world, and then you render back into the image, and then you basically ask that this consistency loss is minimized. So it's not so different than the optimization problems that we had before, but notice that now, like the parameters theta, beta, and clothing are parameterized as a function of the image and the neural network parameters lambda. And this allows us to train over multiple images and videos of people, principle. So these are some examples of papers following this paradigm, and you might check them out. So this paper is basically like the extension of the video avatars paper, but using the self-supervised loop. This paper, MGN, which we'll cover in the next slides, separates the clothing from the body. And this paper called DeepCap, it's subject specific, but it allows to track people in clothing, also including like non-rigid deformations quite robustly from a single video. So if you're interested in these topics, I recommend that you read at least these papers and perhaps related papers. So now there's several works. So for the purposes of this lecture, I'm going to cover this multi-garment net because it's the one paper that separates the clothing from the body, and I want to focus on the advantages and disadvantages of the different clothing representations. So here the goal was to obtain a 3D avatar of a person from single images of a person posed. So the setup is like the same as before, like a person rotates in front of the camera, and then you want to reconstruct the body shape and the clothing from those images. But now you want the ability to like displace the clothing from one subject to another. So you want to reconstruct this subject from the images, get this clothing piece and map it into the target subject, as you can see here. So notice that this jacket is the same, and this jacket is also the same. In order to obtain this level of control, you need a model that separates the garments from the body, as what we saw in the cloth cap paper, right? And now we're going to do this from images, which is going to be more challenging. So in terms of representation, again, similarly as before, you need to cut these garments into pieces and estimate the body shape under clothing. Now, doing so requires doing registration. And this is a very difficult problem, because if it was already difficult with people without clothing, imagine how difficult it is if you have different cuts of clothing, different topologies, different garments, different shapes, different non-rigid deformations. It's going to be even more difficult. Not impossible to solve, but really difficult. So imagine you want to build a model of a t-shirt. You need to segment the scans into garments, estimate the shape under clothing, similar to cloth cap, and now non-rigidly register each garment template to each scan, right? Of course, you're not going to register the template in isolation. You're going to use the body because that's going to make the problem much better behaved. But still, like, this problem is quite difficult. You will need to unpose the scans and, you know, do these things that we've seen several times. And using a sophisticated optimization pipeline, which was quite laborious, we were able to register a data set of 3 people in scans, a 3 people data set of scans of people in clothing. And this allowed you to, for example, take one garment and map it to different scans of people, right? Notice that you have this level of control. You can just change the pants and the t-shirt or jackets. And this is done using cloth cap, basically. You estimate the body shape, you estimate the garment on top, and then you transfer the displacements from one mesh to another, right? Now, the question is, how do you do it with images, right? So the setup is that you have you have 8 images of a person turning in front of a camera, and you have a target scan, and you want this 3D cloth mesh. And how this is done is using this self-supervised loop. You first get the images and you parse them into 2D key points and semantic segmentations of the person. The reason this is done here is because there's not enough data to generalize to all possible variations of texture and clothing, right? So if you send these semantic segmentations to the network as images, like the network will generalize much better to other clothing types. For example, it will not require, the network will not need to generalize to different colors and textures because those are abstracted away on this semantic segmentation, right? Same idea as this neural body fitting. This is applied here. So basically now you have like different heads for each of the garments and a head for the shape and the pose of the person. And then basically you combine these predictions and essentially like you have like, for the garments, like you have a PCA model as well, like where these are the eigenvectors and these are the coefficients. And like this, you can obtain the garment plus some additional displacements that are predicted by the network in order to be able to represent things beyond the PCA space, right? And you combine those like predictions, and then you basically close the loop using self-supervised loss, where you have like an overlap of the semantic segmentation in terms of the prediction and the ground truth. And if you have a little bit of 3D data, then you can also apply supervision on the 3D scans directly, or 3D vertices. And if you have like registrations, right, you can apply a loss on the pose, shape, and translation garment parameters. So this is like a setup which is very similar to this neural body fitting, where we had these different types of losses. And here again, like the observation was that if you have a little bit of 3D data and then additional 2D data, then you can train this using this combination of these two modalities. Perhaps for clothing, you do need more 3D data than for estimating just the pose and the shape. Okay, so now you have 8 input images of a person rotating in front of the camera. Similar setup as before. You can estimate the body shape, the clothing, and then you can apply it to any body shape. As you can see here, these are 3D shapes from the Caesar data set, and those are clothed by just applying the displacements. So perhaps which is what is surprising here is that this very simple and perhaps naive model of just applying displacements leads to quite visually compelling results. So for applications like, for example, like, I don't know, like gaming or sports events where you have to apply like a specific type of clothing to different body shapes, perhaps this displacement idea is just, it's perfectly fine. Right. So one thing that we did observe is that predicting these displacements directly as a function of the image is a hard learning task. And the reason is that these pixels here are in a space that is very disconnected from the space of like vertices. Right? There's no direct connection for the network to figure out what corresponds to what. And this makes the problem difficult. So one way to make the prediction like the learning problem better behaved is to is what we did here in this work that is called text to shape. So which is called detailed full human body geometry from a single image, exploiting UV maps. So the idea here is to turn the 3D reconstruction problem into an image translation problem. So there were a series of papers that were leveraging these image translation networks, which would take an image as input, for example, like a semantic segmentation, and the network would produce, like, for example, like a full image, including texture, and like a realistic image, right? And or, for example, you could give an image of an edge map, an input, and then the network would reconstruct like a full realistic image. And those were like based on this architecture, which is goes under the name of pix-to-pix. And basically, this was very effective. And it turned out that convolutional networks were very good at finding these mappings from image to image, because you have a perfect pixel alignment, like every pixel in the input has a corresponding pixel at the output. So here the idea is to turn this 3D reconstruction problem into an image translation problem. And the question is how you do that. Well, here we leverage UV maps. So for those of you who are still not familiar with UV maps, basically this is an unwrapping of the 3D shape of the person into a 2D image. So the same way as you can unwrap like a world map into an atlas, right? This is exactly the same. You take the 3D surface or the 2D surface embedded in 3D, you cut it, and basically then you unfold it and you flatten it into the image. And how to do this automatically, this is a research topic in itself here. We used an artist design UV map. So there's an artist that knows where to cut the surface and how to map it onto the 2D image. Now, every pixel in this 2D image has a corresponding 3D point on the surface, which means that you can store here whatever relates to the 3D shape. You can store, for example, like displacements, or you can store normals. And the cool thing is that you can have a very high resolution image. And then when you want to render this, for example, like with very high resolution normals, you can just look up the normals in this image, which is much more efficient in terms of data structure than storing the normals on the mesh, because you would need a very high resolution mesh to store all the normals. So yeah, I mean, essentially you can think of a UV map as a convenient data structure, right? Okay, so we know how to represent shapes as an image, because I can store here the displacement from an average smooth shape, for example, like the simple model. I can store at every UV coordinate, like the displacement from the smooth simple model to the target shape that I want to represent, like, for example, like this shape with details. All right, that's the output. And now, how do we get from an image to a UV map, right, representing the image that is aligned with this UV map storing the displacements and normals of the shape? Well, there were papers that were called dense rack and dense pose, and so there were a family of papers that were learning a correspondence map. So they were learning for every pixel in the image, they were learning what is the corresponding coordinate, right, in the UV space, right? So essentially this allowed you to unwarp directly the image into a UV map of the visible pixels. So notice that this UV map is incomplete. It has some missing parts, and that's because like the back of the person is not seen. So now we can leverage this UV transform to go from image pixels into a UV prediction, right, from a neural network. And we have this output, which are the normals and the 3D displacements. And we can, using this pixel to pixel translation network, we can directly learn the mapping from these pixels to these normals and 3D displacements. Now, why are we doing all this instead of just going from the input to the output? Well, because now you have like one-to-one alignment. The eyes in the input are aligned with the eyes at the output, the nose and the chest clothing is aligned with the 3D geometry of the chest clothing, and so on. And this turns out to be very, very convenient for a neural network, because it can look much more at different levels of locality. It can look at local structures and global structures, and a neural network is ideal for doing this. So, so these are some results. So these are 3D renderings of a scan, and this is the ground truth in gray, and this is the reconstruction from the neural network in green. So notice that for the front part, the results look quite detailed. For the back part, it's yeah, it's also quite detailed actually. So to train this, this is based on perceptual losses and also GAN losses in order to obtain details, in order to deal with the multimodality of the problem. For these details, I do recommend that you check out the paper. And although this was trained with only 3D scans of people, this generalizes to images of people in the wild. And what is quite remarkable is that this also generalizes to any or to a wide variety of casual poses. So notice that the pose can be anything, but because these UV maps are, these displacements and normals on this canonic pose, then this is basically invariant, I mean, somewhat invariant to pose, right? Or it's learned to be invariant to pose. All right, so in order to generalize from synthetic data to real data, I don't have time to go into all these details, but of course you need to play with augmentation a lot. You have to apply a lot of different lightings to the 3D renderings, a lot of viewpoints, a lot of shading, and so on. Otherwise, it will just overfit to whatever the lighting conditions of the rendering were for the training process. All right, so this is about reconstructing in one shot using a neural network, 3D avatars of people. And this is much faster than these optimization methods because like the neural network just takes a few milliseconds to produce the output. All right, so we also used a similar idea, and here we learned to map. So one problem was that it's very difficult to obtain textures, a wide variety of textures of people from 3D scans of people in different textures. It's hard to capture. And we realized that there's a lot of clothing images from like clothing stores. And so if we want to learn a model of like possible textures of people, we thought it might make sense to learn to map directly these textures of clothing images directly to 3D models of people. And one additional advantage is that this allows you to do some sort of virtual try-on. And this is what we did. We learned that with a neural network, we learned to map these pixels and the clothing images directly to the UV map of the simple model for different garments. And this allowed you to just take clothing images in the store and then just map them onto the simple model to obtain these textured avatars. Yeah, so if you're interested in this, I also suggest you check out this CVPR 20 paper. All right, this comes to the end of estimating 3D people in clothing from images. So the take-home messages using Vertex displacements, the take-home messages are like video avatars demonstrated that 3D reconstruction of people in clothing is possible from a single video. And if you want to exploit the temporal information, you have to use the fact that the shape barely changes over time. So this is something that you can exploit always. And encoding the body separately from the clothing allows more control. As we've seen, like it allows you to apply, for example, like one garment from one body to another. And it's good to have codes that carry meaning and allow control, like this, for example, like this separated bodies and garments. And we've seen that predicting directly vertices is not so easy, especially if you want to predict detail. And pixel-aligned predictions in UV space yield more detailed reconstructions while allowing you to then, apply different poses to the model, different shapes. We will see another class of techniques which are based on implicit surfaces, which allow, I would say, even better detail than these UV space methods. And this we will cover in the next lecture, where we will cover neural implicits. But this concludes part 2 of this vertex-based clothing and estimating people in images. Now let's take a break and let's continue later with learning a model of clothing. Thank you.